Hi, and thanks to everyone for joining. Today I'll be uncovering an uncomfortable truth. Additive manufacturing will never achieve perfect part accuracy. But there are ways to make the best of these digital approximations that enable the technology. This is the first of 3 pre-recorded webinars on Thinking Additively. Feel free to skip through, replay parts, whatever you like. Obviously, since we're not doing this webinar in real time, if you have questions, please email me at david@additiveblueprint.com and I'd be happy to talk through any questions. I almost always keep these presentations under 20 minutes, but this one has so much important information, I think we might run a minute or two over. I'll begin by describing what it means to think additively and why it's rare to find organizations that are truly thinking about additive design differently than traditional design. I'll go on to describe digital tooling. Digital tooling is the reason that additive manufacturing will always be subject to some unavoidable inaccuracy, called geometric approximations. I'll describe the top 3 geometric approximations that 3D printing uses to achieve design freedom: meshes, layers, and toolpaths. For each approximation, I'll describe how organizations need to be reacting to these realities to make additive work for their requirements. I'll wrap up with the number 1 thing you should take from this conversation. But first, just a little about me. My name is David Busacker, and I'm a designer and an industrial engineer. I began my career in additive as an applications engineer at Stratasys, and I got to know our biggest competitor very well, the status quo. I realized that the entire additive industry needs faster adoption, and that's why I made the transfer to Blueprint, the consulting arm of Stratasys. The mission of Blueprint is to help our customers make sense of how additive, a very big solution, fits into their business, an individual custom problem, in a way that makes sense. Blueprint relies on a 16-year heritage of promoting additive adoption, and it wasn't surprising to discover from one of our recent surveys that about 84% of companies are trying to move additive beyond prototyping, but that the same number feel they're stuck due to additive knowledge. I've heard many frustrated engineering directors lamenting that they're not seeing business value from additive because their organization just isn't thinking differently about additive processes, from design to applications. A traditional mindset on a new technology just isn't fruitful. When we've done organizational consulting for some of these organizations, we usually find that there are 3 disconnects that form this knowledge gap. First, there's a disconnect between the how and the why. Business and engineering leaders both seem to want additive, but for different reasons and with different understanding of its benefit. Then there's a disconnect from reality. Most organizations outside of a small, increasingly skilled and capable center of excellence don't really get how AM works, or even what it is. Finally, there is a disconnect from real tactics that companies can use to create physical value from additive manufacturing. Best practices from design to machine utilization to engineering processes. Blueprint has taken this need to think additively and distilled it down into its 5 considerations on how AM really works. They're called the Think Additively principles, and they govern all 3D printing processes today. This webinar is the first of a series of 3 that will explore the Think Additively principles. We'll be narrowing in on the principle of accuracy, a set of considerations and design tactics that can be used to achieve accurate 3D printed parts. So I'll start with what may be a fairly controversial statement. 3D printing offers complexity at the expense of precision. 3D printing is fantastic for design freedom. It produces parts with short lead times and reduces material waste. It is not known for producing accurate parts. It's just not one of its strong suits. CNC machining and injection molding are much better at accuracy. Why is this? Well, one reason is that 3D printing is still new. The science around thermal expansion and contraction of AM materials and geometries just needs more studying, and what is known is rarely implemented well in accessible softwares. The industry has some work to do here. 3D printing is often used to replace multi-step manufacturing. This reduces cost and process complication, but it means that just one manufacturing process needs to make an accurate part. Whereas in traditional manufacturing, multiple manufacturing, assembly, and inspection procedures provide places to correct inaccuracy and guarantee quality. Finally, 3D printing eliminates the need for hard physical tooling. It doesn't come without a cost. Instead, this digital tooling is used to create parts through a series of flexible, iterative digital approximations. The digital approximations that allow this incredible new manufacturing platform are a feat of technology. They're also inevitable. Next, we will explore just a little deeper this idea of geometric approximation, and then we'll demonstrate the 3 common forms of approximation and how to deal with them. There's a deep chasm between traditional tooling and digital tooling. It's the difference between a hand-polished 200-pound thermoforming mold and a thumb drive with a 3D printing file on it. One is virtually unchanging and permanent. The other is flexible, easily moved, deleted, or improved. Traditional tooling is used to make one single thing, over and over. It doesn't need production flexibility, movability, or really the ability to iterate the design. On the other hand, digital tooling is flexible, customizable, and exhibits virtually no tooling change fees, just the cost of updating a file in a database. It's used to make lots of different parts on the same machine with the same equipment in different batch sizes. Now, with traditional manufacturing naturally comes repeatability. With rigid tooling comes rigid processes and therefore rigid outcomes. Traditional tooling may require hand polishing, a little knob turning, or other adjustments to get what's needed, but once that process is down, it's pretty precise. Digital tooling is naturally more complex, which generally reduces the accuracy and precision of the part. For example, take injection molding. A moderate complexity injection mold takes months to design, manufacture, hand polish, and test, and then rework and hand polish again and test. But once it's running, it makes exactly the same part it was supposed to make. Every defect is rubbed away over the long weeks of hand polishing and fitting. Digital tooling is almost entirely created using automated softwares that turn CAD into parts. The user has to do very little to get digital tooling ready for action, but in exchange, they compromise by allowing the softwares to use geometric approximations to get a part very close to the complete design. Okay, but enough theory. What actually are these digital approximations that are so critical to 3D printing and digital tooling? There are 3 that are shared by almost all 3D printing technologies, so we're going to explore them today and how to deal with them using good design practices. These inherent inaccuracies are mesh approximation, layer approximation, and toolpath approximation. So, for the first approximation, let's look at meshes. Now, I'm guessing most people are pretty familiar with mesh files. They've been around for a long time and are used in all kinds of digital processes, from renderings to video games. Basically, a mesh is a geometric approximation of a complex shape. It takes complex geometric entities like curves, splines, radii, lofts, etc., and generates triangles or squares that approximate those complex math-driven equations. It's kind of like trading quality for quantity. A shape may only be made up of a couple of complex surfaces, or it can be made up of thousands of simple surfaces in the form of a mesh, like you see in the part on the screen. So why is a mesh used over CAD surfaces? Well, like I mentioned, they're very simple. Just a bunch of triangles all touching 3 other triangles in space. And because they're simple, they're non-proprietary or universal, and they are flexible. Basically, since they're just triangles, they can be edited by very simple programs, even in a text editor like Notepad. Finally, it's easy to store color data in meshes. A mesh file is like a rock climbing wall with lots of footholds to attach color data, whereas CAD files are kind of smooth and slippery, making it difficult to assign color and textures. Okay, so let's look at a mesh. This CAD model of a simple 3D printed duct is made up of a few complex curved surfaces, and I'll turn them into a triangular mesh. SOLIDWORKS files are often converted to mesh files before 3D printing, so it's easy to save as STL file in SOLIDWORKS. And you can see here that this is the mesh approximation of this CAD file. Approximations can be a source of inaccuracy, but fortunately you have control over the degrees of the approximation. The math used to turn CAD files into meshes relies on 2 control factors: angular deviation and chordal tolerance. We are not going to go deep into the math on these ideas, but basically, reducing each of these variables is going to result in a tighter, more accurate mesh. But a more accurate mesh, like everything in life, comes with a trade-off. To see that, we're going to go back to our duct model here, export to STL again. Now, if I click on Options, I have a little more control over how my mesh is created. There are a couple of mesh resolution presets here, coarse and fine. There are more triangles in the fine mesh, but it's a tighter approximation. You can also see, though, that the fine mesh is about twice the size in terms of data as the coarse mesh. And if I reduce both of these settings here, it gets to like 5 times the file size. So meshes get really big really quick. Using a mesh that is too coarse is going to look like a geometric approximation. You better bet that the triangles in this coarse STL mesh here on the screen are going to show up in the final part. But on the other hand, large meshes can bog down your computer and add unnecessary processing time to design steps required before printing, like part cleanup, or orientation or support generation. Okay, so here is a practical tactic to help with dealing with mesh approximations. Match the mesh size with your geometry and application. Sometimes it's completely fine to have a mesh lines in a file, especially when doing time and material estimations on a work in progress part. But on the other hand, if you're printing a cosmetic part, especially if it has subtle curves, it's better to err on the side of a large, if unwieldy, mesh file. If your part has complex textures or patterns, the file size is likely to get really large really fast, even on coarse mesh settings. It turns out, fortunately, that the smaller the feature, the coarser your mesh of that feature can be while still hiding the triangles. And when it comes to production parts that will be printed in the hundreds or thousands, it's almost always worth optimizing every element of the design, including the mesh. Another good tactic is just to avoid meshes whenever possible. Many build preparation softwares allow you to import CAD straight into the software, and although they usually perform a meshing operation before printing, it's behind the scenes and allows you to bypass that user error. In addition, some design programs are integrating slicing right into the program, skipping the mesh step entirely. So keep an eye out on as softwares get smarter so you're not wasting time dealing with these unwieldy meshes. Okay, on to the second approximation of additive manufacturing, layer approximation. Now, most people who are familiar with 3D printing know about layers. They are the foundation of every common 3D printing method today. In most technologies, they make an appearance in the final part. And unlike meshes that are being phased out and optimized, layers are basically here to stay. I'm going on the record that we won't see a layer-free additive manufacturing technology hit the market for many years. There have been some advances in non-planar additive manufacturing and 5-axis 3D printing. Those are both mostly FDM platforms. But the two reasons that these aren't mainstream is that multi-dimensional layers introduce a lot more variability into the manufacturing process, and it's honestly just like really tough to program. Okay, so my point is, layers are here to stay. I'm going to show you visually the effect that layers have on your 3D printed part and why they're an approximation of your original design, and basically how you can't avoid them. Let's start with a circle. And let's decide to 3D print this circle standing up. We're going to use the layers on the right to create this circle. So our slicing software matches up the circles to the layers, and wherever the edge of the layer touches the circle, the software makes a cut. Of course, we're doing this in 2D, but you can imagine how this works in 3D. So after the unused layer is removed, the layered part looks like this. Not bad. Actually, it looks a lot like a circle, so we're set. Right? Wrong. That's not actually how layers look. See, the layers are cut in a vertical line and can't curve with the circle. In reality, this is what our layered circle will actually look like. That doesn't look quite as much like a circle. In fact, is it really a circle anymore? All at once, our approximation looks taller than it is wide, and also wider than it is tall, depending on how you look at it. But at the end of the day, it isn't a circle at all. It's not even curved. It's an approximation. Now, layers are definitely a problem for curved shapes like circles, but they can even cause issues for square, straight shapes too, especially when it comes to accuracy. Take this rectangular shape with a cutout, for example. Should the layering process align with the top of the model? Or should the layers start with the bottom of the model? Because depending on how this part gets sliced, the slicer program will assign slices in different ways. In this case, slicing the part from the top on the left-hand side leaves an incomplete or missing bottom layer, and slicing from the bottom, the right-hand side, will cause dimensional problems on the vertical cutout. If you don't believe me, rewind the presentation to the previous 2 slides and check it out. There are really 2 practical tactics for dealing with layer height approximations. The first is to adjust the layer height. This is only feasible with some technologies, namely FDM, polyjet, and stereolithography. But if you're printing in these technologies, you can reduce the layer height to achieve better layer approximations at the expense of a slower build. The second tactic applies to all 3D printing technologies, and that's just to check the layers before hitting print. In the case of this metal powder bed fusion build, some very slight variation in the top surface of the mesh file led to faulty layer generation. This could have been prevented by checking the file before printing. Okay, the third and final approximation we're talking about today is toolpath approximations. I'm going to start with this mesmerizing slow motion video. What we're looking at right now is a metal powder bed fusion build chamber where the laser is just beginning to solidify a new layer. Watch how the individual granules of metal powder are fused to create solid metal. The path taken by the laser to create this shape is called the tool path, and it's another one of the inherent approximations to 3D printing. So a toolpath is the pattern used within a layer to actually add to the growing part. Additive manufacturing technologies use one of the 2 kinds of toolpath methods. The first is called vector toolpaths. Vector toolpaths add to a growing part when a nozzle or laser passes over the shape of the layer in a pattern. When a child has to carefully color a shape in a coloring book, they often will draw around the outside, then scribble in the middle. Toolpaths work the exact same way, involving outside contours and inside infill. The other kind of toolpath that a 3D printing technology may employ is called voxel toolpaths. Each layer in a voxel technology is converted into a pixelated image, deposited onto the layer, typically using jetted ink, and then joined to the rest of the part either using heat or a binding material. Since these pixels are really cubes that are the height of 1 layer each, they're actually called volumetric pixels, or voxels for short. So you'd think that one of these 2 toolpath methods was probably the common one and the other one is niche or emerging, but that's not really the case. The common 3D printing methods today use both methods. For example, in metals, all metal powder bed fusion technologies, SLM, DMLS, powder bed fusion more widely, use lasers in a vector pattern, while metal binder jetting uses an inkjet voxel technology. For the vat photopolymerization family of technologies, stereolithography uses a laser, but its close cousin DLP is a voxel technology. In polymer powder bed fusion, SLS, selective laser sintering, uses a laser to melt each successive layer of plastic to the layer below, while HP's multi-jet fusion and other high-speed sintering technologies use a thermally conductive ink and a heat lamp to create each layer. And when it comes to non-powder bed fusion polymer technologies, the most common being FDM technology uses a vector toolpath. There's actually a voxel equivalent called STEP technology being developed by Evolve Additive. Okay, so why do we care about these types of toolpaths? Well, each comes with their own way of geometrically approximating the layer they're defining, and therefore they each have their own drawbacks. Let's look at vector toolpaths first. On the left-hand side, the toolpaths of a very small FDM feature is shown, and you can see that there are issues filling the beads of polymer into the right shape. Even though there's nothing very complex about this little feature, after creating a contour around the part, there's not enough space to fill it in with any infill. And even if multiple contours are used, like on the right, it doesn't fill in the center. This kind of incompleteness in layer definition, especially when stacked over and over on many layers, is going to lead to a pretty weak part that will probably break. Metal powder bed fusion experiences a different issue with toolpaths: uneven heating. So with polymer PBF, where the inside build temperature is held just under the melt point so that the moving laser pushes the melt temp just hot enough to melt, metal powder bed fusion machines also keep the powder pretty hot, but steel requires a lot more energy to melt than nylon. So as each layer is built, the energy being concentrated on one little point is enormous, leading to internal stresses in the part. Build softwares generate the toolpaths in a distributed way to try to mitigate this, called hatching, but it's not always to overcome the internal stresses. And like you see in this slide here, especially when many thick horizontal sections are built, build warp and even breakage and failure can occur. So voxel-based toolpaths also introduce complications into builds. Generally, these issues are less structural and more visible. One of the most common voxel-based technologies is polyjet, also known as material jetting. The picture you're looking at here looks a lot like the stair-stepping you get from layer approximations, but in fact those rings actually make up the sidewall of that part. That's because as the inkjet head moves back and forth in the polyjet process, it only has a finite number of nozzles from which to eject the photopolymer. The result is that any sloped or curved surfaces that are almost parallel with the head travel direction, usually the x-axis, will show some stair-stepping effects that kind of look like layer lines. The only way around this is really to tilt the part so that it doesn't line up with head travel. Obviously, that's kind of hard to do with a sphere. DLP technology, especially Carbon's digital light synthesis machines, exhibit really amazing build definition. It's known for exceptional build surface quality, and it's one of the most precise 3D printing technologies, though overall accuracy can sometimes be an issue due to material warping. Ironically though, because it builds so beautifully, it's also the easiest to see the voxels. So in this close-up of a DLP part, you can see the interplay between layer lines and the pixelated layers. Unlike on polyjet, where layer lines end up kind of muffled and invisible, all three axes are visible in DLP, which create interference patterns that can be a little distracting, but as you can see zoomed back out, the overall part actually looks pretty nice. So as we've discussed, toolpaths cause different problems, cosmetic and structural, to varying degrees across 3D printing technologies. But the one thing that they do have in common is that they are ultimately unavoidable. So how do you deal with them? Well, the first tactic I'll provide is simply to review toolpaths before building a part. In the case of FDM and other vector toolpaths, small features can become unstable if toolpaths are too wide or too short. Almost all build preparation softwares allow you to adjust laser or extrusion width, speed, and starting and finishing points. Similarly, the second tactic is to review toolpaths in case of failure. This time lapse of MJF parts being built shows just how many layers and how many voxels go into building a full tray of parts. Isolating a failed feature in a failed build and examining the toolpaths used to create it may just be what you need to make a different choice about orientation or, more likely, part design. Like I've said so many times now, geometric approximations are completely unavoidable with 3D printing. It comes with the territory of digital tooling. So we've talked about a lot of things today, but I want to provide you the number one thing: communicate. Having watched this webinar, you are probably among the 1% of people who understand the most crucial elements to design for additive manufacturing: approximations. Communicate these ideas to your colleagues. The number one reason that additive manufacturing remains at the peripheries of most companies is that it is not understood, from a business perspective and from a technical perspective. At Blueprint, our mission is to spread this knowledge, but it's much easier if you do it from within your organizations. Proactively designing for mesh resolution or layer heights or voxel approximations just might be the key to making an additive application successful for your team. Like I mentioned, I'll be doing more webinars on thinking additively. Today was just a part of the design principle of accuracy. And just to give you an idea of how much more there is to learn, this is what the Blueprint Think Additively training looks like that we offer. Accuracy is definitely important, but it's just one of the many things we teach in this class, which is an additive manufacturing design thinking course for engineers, designers, and their managers. Obviously, this was not a live presentation, so please do reach out by email if you have any questions about today's webinar or Thinking Additively. I'm most easily reached at david@additiveblueprint.com, but copy hello@additiveblueprint.com so we can respond even if I'm not answering my email. Again, my name is David Busacker, and thanks for spending the time today.